Hello everyone, welcome to my another lecture on Cauchy's integral formula for derivative of analytic function. This is the lecture the learner will be able to understand the Cauchy's integral formula for derivatives. Earlier I had explained 3 lectures on Cauchy's integral formula. So you have to see that 3 lectures. You can see the lecture of which I have delivered for you. You can see that 3 lectures. Then this is the new topic, that is Cauchy's integral formula for derivative of analytic function. So what is actually Cauchy's integral formula for derivative? This is the formula for Cauchy's integral formula for derivative. When you see, when that is if z, this is dz actually, dz, this is dz, okay, fz dz by z minus z0 whole to the power n plus 1 equal to 2 pi I into f of z0 by factorial n. What is z0? Z0 is the singular point, that is singular point, okay, singular point. So how to get this formula? I'll explain first, then I'll explain a sum using Cauchy's integral formula for derivatives. Okay. So now I am explaining how this formula is coming actually. Okay. This formula is coming from Cauchy's integral formula. This formula is coming from Cauchy's integral formula. This is the first lecture on Cauchy's integral formula. So what was actually Cauchy's integral formula? Cauchy's integral formula was that Cauchy's integral formula, as we had already explained very nicely, f of z0 equal to 1 by 2 pi I integration fz dz by z minus z0. So this was actually Cauchy's integral formula. Okay, now we have to differentiate this formula successively. First, differentiate with respect to z0, then again differentiate with respect to 0, again with differentiate with respect to z0. So we get, so f of, that is differentiate with respect to differentiate with respect to z0 on both sides successively. Okay, so what is this? F dash z0, f dash, this is f dash z0 is equal to 1 by 2 pi I integration f of z dz by z minus z0 whole square, This is first time derivative. Again, if we differentiate this, that means how it is coming actually, z minus z0 take in the numerator, then z minus z0 to the power minus 1, then minus 1 will come first into z minus z0 to the power minus 2 into d dz0 of this, that is minus 1, minus plus 1. By this way, I can explain z minus z0 to the power minus 1, then differentiate with respect to z0, then you will get this. Okay. Again differentiate, that is f double dash z0, this equal to 1 by 2 pi I, this is constant term, integration f z dz, because these are all constant. This is actually, this will be actually 2 by 2z minus z0 whole to the power 3, Okay. So this again can be written as, that is, this is factorial 1 2 pi I integration fz dz by z minus z0 whole square. This again, these two can be written as factorial 2. So by 2 pi I into fz dz by z minus z0 whole cube. Now if we differentiate again, that is f3 z0, then we get this will be 6. Okay, this take in the numerator, then differentiate with respect to z0. This will be 6 by 2 pi I integration f of z dz by z minus z0 whole to the power 4. This 4, this can be written as 6 can be written as this is factorial 3 by 2 pi I integration f of z dz by, here you see, to the power 4. So this can be written as z minus z0 whole to the power. This is factorial 3. So we can write 3 plus 1. This is factorial 2. From here we can write 2 plus 1. Okay. 2 plus 1. Okay. Now if we go this way, then go this way, then what is fn? Actually fn z0. Fn z0 is equal to, this is when it is 3 times differentiate, you are getting here, you see factorial 3, and here is 3 plus 1. When it is n time differentiate, this will be factorial n by 2 pi I, then f of z dz by z minus z0 whole to the power n plus 1. When it is third time differentiation, it is 3 plus 1. When n time differentiation, it is n plus 1. N plus 1. Okay? N plus 1. So this is the actually Cauchy's integral formula for derivatives. Cauchy's integral formula for derivative. Now again, this part can be written as 2 pi I into fn z0 by factorial n. That is, this can be written as again this can be written as like this way. So just follow me. So this can be written as integration fz this is actually c. Okay, c for contour integration, c this is c fz dz by z minus z0 whole to the power n plus 1 is equal to 2 pi I into f n z0 by factorial n. So this is the formula. This is the formula for Cauchy's integral formula for derivative. Okay. When it is suppose n equal to 1, that means z minus z0 whole square. That is first time derivative. Single time derivative. When it is n equal to 2, that is second order derivative. You will get. Okay. Second order, n equal to 2, second order derivative, then you will get here 3. Okay. So by this way we can find. Now the question is, when we have to apply, this is very important part. When we have to apply Cauchy's integral formula or Cauchy's integral formula for derivatives. This is very important. When we have to apply Cauchy's integral formula only or Cauchy's integral formula for derivatives. Okay, that means we have to apply that is if 2 or more power occurs in the denominator. In the denominator portion, that is in the denominator integral, this is the integral, this is the denominator portion. If the denominator portion, the power of z minus z0, that is this power is more than 2 or more power occurs in the denominator, then we have to apply Cauchy's integral formula for derivative of analytic function. This is the first lecture. Okay, so now I will do a sum using this formula, Okay, okay. Evaluate. I'm taking a sum. I'm taking a sum. I am taking a sum from university question paper. So many times came this sum in the university exam. Very important. Very important. Very important. Evaluate. Evaluate cos z by z minus pi I. This is pi I whole square. This power is 2. You see, power is 2. So this integration we have to apply Cauchy's integration, Cauchy's integral formula for derivative, and here C is equal to equivalent mod Z is equal to 5. Mod Z equal to 5, that means this is a z equal to x plus iy, then it will come, that is x square plus y square equal to 5 square. If we put z equal to x plus iy, then this becomes x square plus y square, mod z equal to root over this, then squaring both sides equal to 5 square. So this is the equation of circle, whose center is 0 0, and center, this is x, this is x axis, y axis, this is real axis, or this is imaginary axis. So this is this point is 5 comma 0, because radius is 5. This split to, this is actually 5 comma 0, 5 comma 0, 5 comma 0, this point, and this point is 0 0 0 0. Okay, so this represents a circle, whose center is 0 0 and radius is 5. Center is 0 0, radius is 5. Okay, to get singular point, next part, what will you do? When this is given, then this will represent whether it may be a closed curve. That is, this is actually closed curve. This closed curve may be a circle, may be a rectangle, may be a square. So you have to draw first that thing. Okay, using this you have to draw the closed curve. This is the closed curve. This is the contour, or you can say closed curve. Okay. Now next part, you have to find the, that is singular point. To get singular point, we have to put denominator part equal to 0. We put, that is z minus pi I whole square, this equal to 0, this becomes z equal to pi I. This is the singular point, z equal to, therefore z0 equal to pi I. That is z0 equal to this. I am taking the singular point, that is this z0. This is the z0. Okay, so this is z0 value. So 0 plus pi I we can write, 0 plus pi I, that is equal to 0 comma pi. 0 comma pi means 0 comma 22 by 7. That is equal to 0 comma 3.14. This is the singular point. Why it is singular point? If we, this, for this singular point, this function is not defined. Okay, that is, this integral is not defined when this equal to 0. So this is the singular point. I already explained what is singular point. You can see in my previous video. Okay, now after getting the singular point, what will you do? You have to check whether this point lies inside the circle, inside the closed curve, or outside the closed curve. Okay, so we have to see that this length is 5 comma 0, and this is 0 comma 3.4. That is, this is actually, this point is 0 comma 5. So 0 comma 3.14, this point is 0 comma, that is this point is known as 0 comma 3.14. This point. Okay, so this is inside the circle, inside circle, or inside closed curve C, inside closed curve C, this point. So this point is inside closed curve C. Then by Cauchy's integral formula for derivative, that is this Cauchy's integral formula for derivative. What is fz here? Fz equal to what is fz? Fz equal to cos z. Fz equal to cos z. Okay. Fz equal to cos z. Z0 value, what is Z0 value? Z0 value is 2 pi I. Pi I. Z0 value. Now by Cauchy's integral formula for derivative, that is by Cauchy's integral formula for derivative. Cauchy's integral formula for derivative, this is Cauchy's integral formula. So here is denominator is square, that means we have to differentiate, that is n value we have to put, that is n equal to 1. If we put n equal to 1, that is first order derivative, then we are getting here 2, because here is 2. If it is here 3, then we have to second order derivative, put n equal to 2, then 2 plus 1, that is 3. But here we want to get, that is power is 2, so we have to, that is put n equal to 1. Just I am removing this part, so that is, so what is by Cauchy's integral formula, that is C, what is fz, that is cos z dz by z minus, what is z0, z minus, that is pi I, z minus pi I whole to the power n equal to 1, that is 2, n equal to 1, 2 pi I into f dash z0 by factorial 1. Okay, factorial 1. Now how to get this value? That is 2 pi I by factorial 1 is 1 into, what is fz? Fz is this cos z, so f dash z is known as minus sin z. F dash z is minus sin z. So that is f dash, what is z value? Pi I. F dash pi I is equal to minus sin pi I. So f dash z0, that is equal to f dash pi I. So f dash z is equal to minus sin z. F z pi I equal to minus sin pi I. So answer is 2 pi I into sin with negative sign, because it is my f dash pi I equal to sin pi I. So this is the answer. This is the answer for this integration. Okay, I think everybody understand very nicely. So this is actually Cauchy's integral formula for derivatives, and how this formula applicable. So I have taken a sum in this lecture. So I think it's clear to everyone. So I'll come with my next lecture, that is solve problem. I will take 2 or 3 sums in the lecture number 2 of Cauchy's integral formula of for derivative of analytic function. Lecture number 2 to 3 or more sums I'll solve. If you like this video, then share it to all of your friends. Till then, bye bye. Thank you.